Hello, in this video I'm going to quickly bring together what I've said about the laws of thermodynamics in other videos, because it's just nice to have it all in one place, particularly if you've just come to looking at some of these. Well, this might be the point that you're starting at, and then you can go out to those other videos. Now, as I've said many times, the laws of thermodynamics have got a lot of nuance and a lot of depth to them. They're difficult to grasp in terms of exactly what they mean and how to apply them and why they're so important when you first start out in thermodynamics. In fact, I mean, they can be pretty difficult to grasp even when you get further into thermodynamics. And that is why they don't get spoken about that much before you head off to university, because it just is hard to see the point of them. Anyway, I've tried to chip away a little bit more below the surface on these. So I'm just going to summarize what I've been saying so far. So we've got four laws which go from 0 to 3 because they thought of the first one on the list, the zeroth law, after they'd already fixed the others. So we got the zeroth law of thermodynamics. So this is the thermal equilibrium one. If you've got substance A is in thermal equilibrium with substance B, and then substance B is in thermal equilibrium with substance C, then that means that A and C are in thermal equilibrium. So if we've got that in equilibrium and we've got that in equilibrium, then the consequence is that is in equilibrium. This does get mentioned usually when you're doing your A-level physics, and it seems ridiculously obvious because we approach this generally in terms of temperature, thinking, well, of course, that means A and B are the same temperature, B and C are the same temperature, and that means A and C are the same temperature. It's blindingly obvious, it seems. But of course, that is already based on the fact that we're assuming one of the outcomes of this particular law, in that we can have this common temperature scale that we can set up, because all of this heat, all of this thermal energy we're talking about is all the same. It's all measuring the same thing. We don't need a different scale for each substance. It is the same scale that we can use. So once we've already got that assumption, which is what we're generally approaching this with when we see it the first time, then yeah, it seems obvious. But what I've been trying to build this around, which is why I mentioned this in the video on setting up temperature scales, is that this is one of the consequences, is that we can have a common temperature scale. So that's what we're going for on that one. Right, then we've got the first law, which is often seen as the conservation of energy law. And again, you think, well, okay, we already know this. You see it, it's just another statement of conservation of energy. And yeah, in some ways it is. But as I was saying in the summary video, when we're looking at the changes of state and going through phase transitions and such like, when you're putting energy into a substance and taking energy out of a substance, it's getting us to look beyond just the straight heating cooling distinction of our radiation, conduction and convection. And it's also including the work in and work out that can be done on a substance or by a substance. So we've got these two methods of getting energy in and out of a substance: the heating, cooling, the work in and work out. So the work one, the good example is either compressing a gas with a piston or something similar, or using a gas, getting the gas to expand and then push the piston upwards. So that's the much more of a mechanical work approach to how we can get energy in and out of a substance. So we're making the distinction of there's these two methods of energy transfer, and then of course that if we're putting energy into something, then the conservation of energy means we can get exactly the same amount of energy back out again. It's all part of the same thermodynamic processes. There's not something being lost along the way. We can heat something up and do work on it in order to increase its internal energy, and then we can reverse the process, go back to exactly the same starting state that it was in, and recoup the same amount of energy. So we've got two sides of that first law of thermodynamics. Then we've got the second law of thermodynamics, which is the one that a lot of people get very excited about. This is the entropy arrow of time law of thermodynamics, saying that entropy is increasing. That's the, as we go through time, entropy will increase. So you've got that as a basic statement of there is a difference between the past and the future. But then we were talking about it in terms of energy and saying, well, if you've got a higher concentration of energy, then that energy will spread out into areas of lower energy. So we're saying really that energy spreads out. That is the tendency for things. So we can apply that to our physics in general, saying that energy spreads out. We can also say that, you know, hot goes to cold. That's the direction of energy transfer. We don't get things going from cold to hot. And of course, this is what all of our industry was built on, really. You know, you think of all the stuff that we use, like steam turbines and things like that, it's all based on this idea that we're getting hot going to cold. You know, if we couldn't rely on that and we didn't have this is how energy behaves, you know, mechanism and law behind it all, that energy is spreading out and is going from hot to cold, then, well, none of that would be working. So it's a profoundly important and deep law, this one, that is adding this difference between past and future with the arrow of time, because entropy is increasing with time. And yeah, also this idea of what's happening with energy. So that's our second law. The third law, which is the absolute zero law, so hence why I was talking about this in the video on absolute zero. This is the one, again, linked to entropy, where we're saying that entropy will, as you're reducing the energy, as you're reducing the internal energy of a substance, that entropy will approach a constant value. And it's a consequence of this that we end up with this absolute zero that can never be reached, because you can only get a change in temperature if you've got a difference in entropy. So you can never quite get there. It's like, you know, the entropy will be approaching asymptotically a particular value as we're reducing the internal energy of the substance. You never get there. It's the frog jumping halfway to the wall situation. You're getting closer and closer and closer, but you never actually get there. So it then predicts this absolute zero, the existence of absolute zero, where we've got the minimum internal energy, where we've got our minimum temperature, but it also tells us that we will never actually be able to reach absolute zero. So there's a lot more to those laws than just those things, but that's what, at least what I've chosen. I mean, you know, maybe people would pick different things as being the key points of these four laws of thermodynamics, but I've chosen those at least being a starting point of, well, why is each law important and why is it more than it may look like when you just see it for the first time, particularly for the zeroth and first laws, which just look ridiculously obvious when you first see them. So yeah, hopefully that's given you a little bit more of a foothold on the four laws, but just keep in mind, as with so many of these things in physics, there is a lot of scope for deepening your understanding of what these laws are actually about. So there you go, that summarized all of those.